Swayam Prabha. Digital India. Educated India.
Hello, so let's get started with the week 8 lecture. Remember that we have started with reinforcement learning in week 7. We defined the reinforcement learning problem, right? And then I told you a few applications. I hope enough to convince you that we are looking at a very relevant problem that agents face when they have to deal with uncertain environments in which they learn. So, reinforcement learning is the abstraction of doing that, of doing sequential decision making based on experience by trial and error. So, what we are now going to sink into is the conceptual framework, right? The mathematics, the abstraction, okay, that we are looking at using MDPs and such. So, this week's lecture will continue from last week's. So, the plan for this week is to begin by revisiting the problem definition. Okay, what is the reinforcement learning problem? So, I want to go into a little bit more detail this time, right? Because there are two flavors of this problem that we will study. One is called the prediction problem. The other one is the control problem. Okay, so control is actually what we described last time, but we will anyway spell out both of these to get begun with this lecture. And there are some differences between learning and planning. All right, so we did MDP planning, value iteration, policy iteration, linear programming, where we were given the MDP. Things get a little bit more challenging when you are not given the MDP, when you have to learn from experience. So we will also make explicit a few assumptions that we have to make on the underlying MDP in order to be able to solve the reinforcement learning problem satisfactorily. Then we will get to business. Okay, so as a part of this lecture, we will consider an algorithm that actually solves the reinforcement learning problem. It's very simple, direct. It's like the first thing that would come to most people's minds. So we will present that algorithm, and thereafter, I mean, we will become a little bit more realistic, right? Trying to devise algorithms that are more efficient, right? That have more of a sort of intuitive basis, and we will do that in this lecture in the context of prediction, okay, which is one of the problems. Similar ideas will also apply to control, and that's really what is going to follow through the rest of the course. Okay, so again, what is the reinforcement learning problem and what do we mean by prediction, control, etc.? So let's just quickly review what we said last time about reinforcement learning. There's an agent and an environment, right? And the environment is being modeled by an MDP. The only thing is the agent does not know what that MDP is. It probably knows the states, the actions, the discount factor, maybe sometimes the rewards, but crucially, it does not know what happens when you take an action. Okay, so the way the agent learns about the world is by actually taking actions from states and seeing what happens. So the agent takes an action, the environment comes back with a next state and a reward. So at any point of time, the agent has seen what has happened so far. From some state, it took some action, it got a reward, went to a next state, and that kept happening. So it's piecing together a little bit, right, based on this history, how the environment might be. And based on this, the agent has to decide what to do in order to maximize its reward. So it depends on history for doing this. Okay, so this is from last time. Now let us get a little bit more formal in defining what is the control problem. Okay, control problem is again the problem that we formalized last time. So at any point of time, the agent has its history to consult, and when we say agent, right, maybe you can also formally say it's a learning algorithm in the sense that it maps histories to actions or maybe distributions over actions. And again, the separation of duties is the agent will look at history and say which action it is performing. The environment will take that action, apply it on the current state, and see what reward and next state that you get, right, based on the underlying MDP. So the MDP is to be thought of as the environment, right, because it has the transition probabilities and the rewards. The agent is in charge of the policy or the learning algorithm that maps state to action or histories to action. The question we specified last time was, can we have an algorithm L such that if you look at the number of times it is taking optimal actions, right, for the corresponding states that it is visiting, that number as a fraction of the total number of time steps should tend to 1. Okay, with more and more and more experience, you should start taking optimal actions. So is it possible to construct such an algorithm? So this is what we called the reinforcement learning problem last time. It is the reinforcement learning problem, but more specifically, it is the control version of the reinforcement learning problem. Okay, so control is a standard word, right? Control means the job of taking actions. Okay, so there is control theory, an entire subject that looks at what is the right response to a particular situation. Right, the agent's job is to specify what to do, and that's why this is called the control problem. And for understandable reasons, there is a second problem, which is arguably an easier problem. Okay, that's called the prediction problem. And almost always you'll look at prediction before you look at control. Okay, prediction is usually like a stepping stone to control. We have sort of presented these in the opposite order because control is eventually the problem we want to solve. Okay, prediction is like a step in the way of doing control usually. Okay, so the main difference between control and prediction is, in prediction, the agent is not asked to decide which action to take. The agent is given a policy pi that it is going to follow. Okay, so let's assume it's a Markovian stationary policy. It could be deterministic or it could be randomized, but the agent's behavior is fixed. Okay, so we know that the agent is going to be following some policy pi. The agent's job is to estimate the value function of pi. Okay, what it's going to try and do with experience is say, well, this is what v pi is. Okay, so again, what the agent can depend upon is history. Okay, state action reward, state action reward. But to note in the context of prediction is that the actions are taken according to this given policy. Okay, it's not the agent does not have arbitrary sort of control on which action it can take. Actions are being generated. I mean, if you want, you can think it's being generated by the agent, or maybe it's happening by default or something like that. But pi is being followed. Okay, so of course there is no question about taking optimal actions or anything like that. The actions are fixed, and so the job of the learning algorithm now is to look at history and come up with an estimate of the value function of pi. Okay, so at any point of time, what the agent does based on history is it gives estimate of v pi. Okay, let's just call that v hat t. Right, after maybe t steps of interaction, it's got an estimate. Let that estimate be v hat t. So the question is, and this is the prediction problem, can we have a learning algorithm L that assures us that v hat t, right, in the limit of t going to infinity will converge to v pi. Okay, we want that with more and more and more experience, you're able to put your finger exactly on what the underlying v pi is. So remember, this was actually the problem of policy evaluation when we were talking about planning, right? You could do this by solving Bellman's equations, but remember Bellman's equations had on their right-hand side the transition probability matrix, the reward function, right? So you don't have access to those, okay? And it is based on interacting with the MDP that you have to now estimate v pi, okay? So prediction is basically policy evaluation in the learning context. So one thing to mention is we are being a little bit hand wavy when we are saying that we want an algorithm L that is such that v hat t will converge to v pi. See, that's because v hat t is a random variable. Okay, so what do we mean by saying the limit of this is v pi? Right? V pi is given MDP and policy, it's like a fixed vector, right? So you have to be a little bit more specific when you're saying a random variable is converging to something. So it's okay for all practical purposes, I think, to not worry so much if you intuitively understand what is going on. But if you want to be very precise, right, maybe the definition that we should apply is convergence in probability. Okay, that means you give me any epsilon and delta greater than 0. Okay, then what we want L to achieve is that there must be some time t naught beyond which, okay, for all t that is greater than equal to t naught, the probability that the, let's say, max norm between v pi and v hat t exceeds epsilon. Okay, that should be smaller than delta. All right. So after a particular point of time, you draw any epsilon ball around v pi. You specify any delta for me. There must be a time t beyond which, with probability at least 1 minus delta, you will be inside of that epsilon ball. Okay. So this is formally one definition that we can go with, but we will not be getting too technical mathematically in the reinforcement learning context. I mean, we did a little bit of this in the context of bandits, regret, etc. Our intent more, okay, in this part of the course is to actually look at how to put these ideas together to construct algorithms, agents that can solve many problems. So we will be a little bit less, I don't know, particular, technically rigorous when it comes to notation. Okay, but I think that's okay. If it comes to it and you have to work out something, right, you should have the confidence of being able to figure it out. Okay, so we have defined these two problems now. We have said reinforcement learning usually is about control. You want to learn which actions to take so as to maximize your expected long-term reward, right? Or the way we have stated it is you want to have an agent that makes a sublinear number of non-optimal decisions. Okay, that's control. Prediction is the easier problem where your behavior is fixed. What you want to ask is what is the value of this behavior? Right? If this policy is fixed, what is my value function? Presumably, that is also something that you can infer from experience, right, and refine with time. Now, can we solve these problems? Is it even reasonable to expect that you can have learning algorithms that can solve the prediction and control problems? More or less, yes, but we have to be a little bit careful, okay? And in what sense do we need to be careful? In the following sense, that's like what's coming up on the next couple of slides. We need to assume that the MDP is sort of conducive for being able to do this, okay? So formally, I'm going to provide two assumptions. So going forward in this part of the course, we will assume that the MDPs we are given satisfy these assumptions. Okay, if they don't, then it's not really very reasonable to expect to solve these problems. So what are these assumptions? So the first is technically called the property of irreducibility. Okay, irreducibility means you cannot be reduced. Okay, so there's a lot of text going on this slide. So before getting into that, let me actually just give you the intuition, okay, what's going on with irreducibility. So look at the MDP here on the left, okay, the figure. So what's going on is I've just drawn, let's say, the arrows, the transitions which have non-zero probabilities, okay. Any arrow that is being drawn here corresponds to a transition that will happen with non-zero probability. So let's not worry about the rewards. In fact, let's not even worry about the discount factor right now. Now observe in this left side MDP that if you take the action blue from S3, okay, let's say you actually also take blue from S1 and S2. So let's say you're following the policy blue, 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 okay, blue from here, blue from here, blue from here. What's going to happen? Right? What's going to happen is within 1 or 2 steps you will be in S1 and you'll never get out of S1. Right, because there's a deterministic transition self loop at S1. So on such an MDP, it's really not feasible for us to learn, right, about, let's say, the value of taking action blue from S3, right? I mean, it's something that will happen only once. You are not sure whether it's a deterministic transition or you just got lucky and it happened, but you're going to be trapped in S1 forever, right? So on such an MDP, how is it even possible for you to learn from your history, like what is the value of, let's say, S3's action, right, or S2's action? It's not a reasonable thing to do, right? On this MDP, on the other hand, on the one on the right, you will see that whatever policy you follow, right, whether you're doing red or blue at S1, S2, S3, you will always come back to your original state. So from any state, right, you will be able to go to every other state, right, and then come back to your state. There's sort of full mixing that's going on. There's no separate classes of states that you get into one, you won't go into the other. So this is basically the idea of irreducibility. Okay, the second MDP is not reducible. or irreducible. The first one is reducible. So now let's look at the formal definition. So let's fix an MDP and a policy for that MDP. Okay, there's M and there's pi. Draw a graph as I have drawn here, in which you are drawing a line corresponding to every non-zero transition. Okay, so for example, from let's say S1, right? If you take red, you can go to S1 with some non-zero probability. You'll go to S2 with some non-zero probability. Those are the two things that can happen. So this is the graph that we draw. Okay, it's a directed graph because of the nature of the transitions. So now, looking at this graph, you can ask the question, for every S and S prime, okay, is there a directed path? Okay, so you are fixing the MDP, you're also fixing the policy. Okay, so you're either fixing red from here or blue from here, red from here, blue from here, or red from here, blue from here. Right? You fix a policy, so you'll only be looking at some of these arrows. But whichever policy you're looking at, the question is, are every S and S prime connected by a directed path? If yes, okay, then M is irreducible under that particular policy. Okay. On the other hand, if there is not, then M is not irreducible under a particular policy. If there is even a single policy for which M is reducible, right? It's not irreducible. Then M itself is reducible. It's not irreducible. Okay. So like that's the definition. So it could happen here. I don't know if it is. Maybe for some policies you'll actually visit all the states, right? But at least one policy, right? Blue, blue, blue. You can see over here. That's not happening. Okay. You can't, let's say, go from S3 to S3 by taking blue from here and blue from here and blue from here, or S3 to S2 also. Okay, so this is irreducibility, and you've already seen why we need this. Okay, unless you're able to visit every state often enough, you're not going to be able to, that basically means infinitely often, you're not going to be able to induce its, for example, do prediction, right? Find out what its value is, unless, basically you need the assumption of irreducibility. So that's assumption number one. Assumption number two is not nearly as crucial for us right now. Okay, but I'm giving it to you anyway because it is something that we will possibly use in the later part of the course. This is somewhat more technical, and this is the notion of aperiodicity. Okay, so periodic means something happens at time step 5, 10, 15, 20, right? That's periodic. So aperiodic means it doesn't have like a period like that. Okay. So what is aperiodic? Again, let's do the intuitive explanation first and then do the technical definition. So again, you can see these two MDPs. Okay. In fact, these are MDPs with just one state, right? One action. Or you can think of this as an MDP in which the policy got fixed, right? And therefore, you only see the arrows corresponding to that policy, whatever. Okay. But if you look at the one on the left, imagine that you started at state S1 the first time step, then you're going to be in S2 the next time step, and then 2 steps later you will be in S1. Okay, and then again, 4 steps later you will be in S1, and then 6 steps later you will be in S1. You will never, so suppose you were at S1 at time step 0, right? You will never be at S1 on an odd numbered time step. You will only be there on even numbered time steps. Right? This MDP on the right, on the other hand, imagine that, and by the way, on the MDP on the left, the same is kind of happening with S2 also, right? If you're in S1 on even numbered, then you'll be in S2 on odd numbered, and vice versa. S1, on the other hand, has a self loop going on over here, right? But imagine, because of that, what's going to happen? There is nothing to say that you'll only be in S1 on even numbered or odd numbered time steps, because, I mean, if you just happen to execute this self loop, right? It might happen because of the randomness. There is some chance, right? Some non-zero chance that if you're here, you'll be here the next time step, and then you will start going to S2 after that. Okay, you don't have this 2, 4, 6, 8, 10 kind of thing that's happening with the first MDP. So the MDP on the left is called periodic. The MDP on the right is aperiodic. Okay, now let's look at the formal definition. So again, let's take an MDP and some fixed policy pi. Okay, this definition is going to be a little bit, it's not very easy to read and understand, so maybe you'll have to do this a couple of times, but let me try my best. So for every state and every t greater than or equal to 1, okay, so t is going to be like the number of steps that you have executed, let us say. Let x of s and t be the set of all states, okay, so x is a set of states. X is a set of all states s prime that there is a non-zero probability of reaching if you start at s and follow pi for exactly t steps. So you start at s, you follow your given policy pi. X of s1, right, is the set of all states you can be in after one step. X of s2 is a set of all states that you can be after 2 steps, 3, 4, 5, etc. Okay, so x is a set of states. Y, okay, which is going to be defined in terms of x, is not a set of states but a set of time steps. Okay, it's a set of integers t. So y of s is the set of all t such that s itself is a part of x of st. Okay, so let's just do this with this example. So let's suppose the state we are considering is s1, right? So what is it? Capital X of s1 and 1 time step, it is s2. And 2 time steps, it is s1. 3 time steps, it's s2. 4 time steps, it is s1, etc. Right? So what are all the t's for which x of st contains s itself? In this case, it's going to be 2, 4, 6, etc. All right? So y is that set of all t's. Now, it looks a little bit odd for something like GCD to be coming up here, but that's what we're going to apply. Okay, so y of s is the set of all these time steps, right, at which you can come back to your starting state. Let p of s be the greatest common divisor of these time steps. Okay, so here's the definition. Okay, if for all states p of s is 1, okay, then m is aperiodic under pi. If there is even a single state for which p of s is not 1, right, it means it's greater than 1, then m is not periodic under pi. So what is the GCD of 2, 4, 6, 8? It's 2, okay, and that's different from 1, and therefore this MDP is not aperiodic under this policy. Well, there's only one policy here. Okay, so actually y of s2 also in this case will be the same thing. Okay, 2, 4, 6, because you can come back from s2 to s2 in 2 steps, 4 steps, etc. But even if there's just one state, right, for which p of s is not 1, then m is not aperiodic under that particular policy. Otherwise, we look at all policies. If m is aperiodic under all policies, then m is aperiodic, full stop. Okay. What's going on with the MDP on the right? So you'll notice for S1, right, the number of time steps after which you can come back with non-zero probability is 1, 2, 3, 4. Okay. So you can come back in 1 step because of the self loop, 2 steps, 3 steps. So sometimes you can go to S2 and come back, but otherwise because of the self loop, you can just sort of stay put, right? So S1's p value, right? P of S1 is just 1. S2's p value is the GCD of 2, 3, 4, 5, right? You can come back from S2 to S2 in 2 steps, 3 steps if you had done one self loop over here, 4 steps, 5 steps. So it doesn't matter that you're starting at 2, right? But the GCD of 2, 3, 4, all the numbers is still 1. And so this is an MDP in which the MDP is aperiodic. Okay. So again, aperiodicity is an interesting property. We don't need it, in its full form all the time. Okay. But for some of the later lectures, it's going to be useful to consider aperiodicity for the reason that if an MDP has both properties, okay, it is irreducible as well as aperiodic, then such an MDP is called an ergodic MDP. Okay. Ergodicity is this property of being both irreducible and aperiodic. Now, the good thing about an ergodic MDP is it has what is called a unique steady state distribution under any policy. Because you take an MDP and you fix a policy for that MDP, then that policy induces what is called a steady state distribution. So what's a steady state distribution? So let's denote for policy pi the steady state distribution by mu pi. It's a distribution over the states. Okay, and so it's a distribution. Therefore, I mean, if you sum it up over the states, it's got to sum up to 1. The idea behind a steady state distribution is it doesn't matter where you start, like whatever your start state be. If you spend long enough in the MDP following this policy, then at infinity, right, there will be a fixed probability with which you will be in every state. That probability is precisely what is called mu pi of S for state S. So if you want to do this formally, right, let P of S comma T be the probability of being in state S at time T when you're following pi. Now, of course, if you want to say this precisely, you also have to say where you're starting, right? Because where you're going to be at time T after by following pi for, the probability of being in state S by following pi after T's time steps of starting must depend on where you are starting. So the good thing about ergodicity is it doesn't matter where you started. If you look long enough, okay, if you take the limit of t going to infinity, then P of S comma T will be the same for all start states. Okay, it doesn't matter where you started, you'll sort of forget that. And that probability is what is called mu pi of S. Okay, so ergodicity is something that we will probably encounter a little bit later. We're not going to need it right now, but given that we are stating the problem here, right, I thought I'll include it as a part of the assumptions that we are making. So again, what have we been doing in the last few minutes? So we formally defined the problems of prediction and control and said, well, we have the constraint of having to do this in the learning setting, right? You have to interact with the MDP and figure out what its value function is or what is the right way to take actions. And that you cannot really expect to do if you go from one state to another, you'll never come back, right? So irreducibility gives us the guarantee that you will visit every state infinitely often. If you spend infinitely often an infinite amount of time in the MDP, doesn't matter what you do, you'll keep revisiting. Aperiodicity also tells us that not only will you revisit, you will not be visiting any state at time, 3, 6, 9, 12, right? You will actually be visiting it at time steps which don't have like a period that's greater than 1. And therefore, it will follow that the MDP is also ergodic. Okay, it will have a steady state distribution. Steady state distribution is something that comes quite often in slightly more sophisticated, not sophisticated, but maybe slightly more complex settings, okay, in which we will study MDPs. Okay, so we are done with that first part. And what we are ready to do right now is to look at a way of solving these problems, right? How do you solve the prediction problem? How do you solve the control problem?